Welcome. My name's Samuel Watt. Today I'm going to be making a case for using relational databases in our serverless applications. So a little bit about my backstory. It's somewhat relevant to the talk. So I entered the AWS in the serverless space in 2019. I decided to leave. I decided to leave my graduate job of 2 years to try and create my own company, try and bootstrap with serverless. I learned how to build Lambda functions. I learned all about AWS in the cloud. And then 1 year later and one pandemic later, I found myself needing to find a real job. So I joined a startup as a DevOps engineer. They had some Python applications using the Django framework, and they essentially needed all of that in AWS. So I spent 2 to 3 years working with CloudFormation, deploying EC2s, containers, and this is where I got my introduction to RDS, the Relational Database Service. So that was my first opportunity to work with these things firsthand. In 2023, I had the itch to get back into serverless development. I missed my Lambda functions. So I left and I joined Serverless Guru as a serverless developer, which is where I still am today. Earlier this year, my role in the company slightly changed. I went from being a developer to moving into solution architecture. So I'm now sort of making those design decisions for our clients' products rather than building them myself. A fun little fact about me as well, around 2020, I decided to pursue the digital nomad dream, and I moved to Costa Rica and discovered surfing, which I would do almost daily. As you can see, I'm not quite as tanned as I should be, so in 2023, I did move back to the UK, and guess what? I still can't surf. It's a really, really hard sport. So what are we going to talk about today? I've broken the talk into about 3 different sections. So first of all, I'm going to tell you all why relational databases really, really suck for serverless applications. There are so many reasons why on paper we should avoid them at all costs. We'll debate some of them, but some of them I'll hold my hand up for. Then we're going to sort of turn the tide of the talk, and I'm going to give you some points that maybe you haven't quite considered in the real world to using relational databases. This is where I put on my solution architect hat, when you really do need to give a fair trial to all of the different possible tech stacks to choose from. It's been mostly a comparison with DynamoDB. Spoiler alert, in case that wasn't too obvious. And then the final 10 minutes, I'm going to give some tips and highlight some tools that can help with the developer experience once you've made that decision to go with a relational database in your serverless application. And maybe some time for Q&A, I guess we'll see. Okay, so first of all, let's start. Why relational databases don't suit serverless. I really am going to break down relational databases so much that it's going to have no self-esteem left after these 4 points. So our first point, we hear all the time, relational databases don't scale. I'm going to hold my hand up for that one. They really don't scale that well. Let's sort of ask ourselves why. SQL, this is a bit of technology that was created in the 70s. Nowadays, we typically would use MySQL or Postgres for our database engines. Those were invented and created in the mid-90s. So I'm not going to blame the creators for not going with a cloud-first mentality when designing this software. The software is designed to run in a box, everything, sort of the compute, the persistence, the storage layer, everything's really designed to be in one box, which isn't very cloud-friendly. So when we say it doesn't scale too well, that's because these relational databases probably need vertical scaling rather than horizontal scaling. Vertical scaling means we take an instance and we need to increase its size. Now, most of the web applications in the world, they do use relational databases. So it's clearly not a showstopper that they don't scale. So why do we care particularly for serverless applications? On the left-hand side here, I've highlighted some of the components you typically use in a serverless application. We've got those entry points, our API gateways, our queues, our event buses, our load balancers. Once some kind of request or event comes in, we typically need to compute. So Lambda, our functions as a service, our workflow orchestrations, or some containerized solutions, maybe using AppRunner or ECS. And then you would normally need to store some data somewhere. So we've got our document storage and something like DynamoDB, S3 for our object storage, DFS for file storage, and then relational databases for our table storage. And if I were to ask you to identify which of these services are known for scaling very, very well and handling spikes in traffic, which is what we all know serverless applications are good for, the answer would look like a little bit like this. So most of these services, entry point, compute, and storage, they will handle scaling very well. The elephant in the room, relational databases don't. So why is that such a big deal? Well, we've introduced a bottleneck. There's no point having a Lambda function behind an API gateway designed to handle a burst of 10,000 requests in the space of a few minutes. If those Lambda functions are all going to try and make a request to a database and things get throttled, those requests don't make their way through, the application comes down. Our second point, the relational databases are slow. At this point here, I'm going to slightly contest, because it's not really a very fair comparison to make. Most people will be comparing running applications with relational database versus something like DynamoDB. DynamoDB, very, very fast. So I'm going to try and fight the corner of relational databases using an analogy. So relational databases and running any kind of database is a bit like running a bar. You've got our pubs, our wine bars, gym bars, and all sorts. You have people coming in with requests, and you serve requests. You serve them drinks, or you execute a database transaction. Now, picture this as a scenario for a bar. You're at a sports event, and what happens at halftime? You have 10,000 angry sports fans cramming into a tiny room trying to get their halftime pints. And what does that bar look like? Hopefully this is going to work. It looks a little bit like this, especially in the last 5 or 6 years. We have these automated machines that are just pouring pints for us. We're taking money and we're just giving out pints. So as somebody wanting to get your drink, like somebody trying to make a database request, you get to the front of the queue, you look at the menu, and you can choose from a beer and a cider. So we have a very restricted set of access patterns. We have a very restricted menu. You ask for a pint and it's given to you. Now, there we go. Now let's ask ourselves what, and I don't think that was particular, that was what a DynamoDB would look like in this analogy. Okay, you have a very restricted set of access patterns. You need to design your database in the right way to meet those access patterns, and if you do, it's very fast. Now, where do relational databases live in this analogy? Some people who associate with being slow would say, well, we've got this bar that we're running at the sports event. Let's replace the pint with something like Guinness. For those of you that don't know, Guinness, very slow to pour. Imagine having 10,000 angry fans coming in at halftime and all having to buy Guinness. You're not going to be able to serve those requests in 15 or 20 minutes, are you? It's simply not designed for that. But that's not what relational databases would look like in this analogy. Instead, they're more like a cocktail bar. So you turn up to a cocktail bar, you ask for some tutti frutti margarita, and you have to wait maybe 5-10 minutes. You have the bar staff, they have to go and cut all sorts of fruit you've never heard of. They've got to shake something here, shake something there. And then 5-10 minutes later, you're given a tiny glass with a bit of red liquid, and that's your cocktail. Now, if you had to compare the performance of that cocktail maker versus our DynamoDB bar staff with those automated pints, you can't say that one's faster than the other because they're doing different things. And so why is a relational database like a cocktail bar? Well, because relational database can do very fancy queries. You can join, you can do almost anything in sort of your filters. It's very powerful what you can do. And looking here to the ACID compliance, which is what most databases strive to be, the I stands for isolation. That means that for every transaction, it must run in isolation. If you've got other transactions trying to read and write data, it should not influence what your transaction is about to do. So that means you've got to lock all sorts of rows that you're reading and you're writing from. And so imagine in a serverless application, you've got 1,000 lambdas running at once, and they're all trying to write or read from the same tables. And you get into this fight for locking, and these internal queues get built up in the database. And as a Lambda function, you think this database is slow. In reality, what you're doing is something quite complex, and it's something that DynamoDB doesn't support. You can't do a join between two tables. And so it's not a fair comparison to make. I'm sure if you were to create a basic CRUD API using DynamoDB as a database and a relational database as your database, the performance would be comparable. I'm not sure which one would be fastest, but the key point for this slide is that we're doing different things. So to summarize, relational databases in cocktail bars, don't think Guinness. Our third point, relational databases require a VPC. Again, I could bring up that list of components and ask you which of these require a VPC, and you would have got a similar result. Almost all serverless-friendly components, you don't need a VPC. And coming from a developer background, it's just less for me to do. But when you creating a VPC is one of the first things you do when you're learning the cloud. One of the first things you do in the console or in CloudFormation. So that's not really the main pain point for me as a developer. It's more so when I'm running things locally. When I'm working locally, I can use my my DynamoDB that's in our development account. We can reproduce a bug, set up some data in a certain state, and I can use it. I can invoke my lambdas locally, and it's very fast feedback loop. When I have to work with relational databases, I need to probably take a dump of the data, somehow extract it from our VPC into S3, and then I've got to download it to my machine, and then put it into a local instance of a database. So it's a pain. I've just highlighted some of the architecture differences here. So on the left-hand side is what it looks like to use DynamoDB. Because it's exposed as a HTTP API, we've got our Lambda functions that don't have to run in a VPC that you've configured yourself. Whereas on the right-hand side, because we're using the database port and protocol, and it's using that underlying networking of a VPC, annoyingly, your Lambda functions do need to be run inside VPC. This used to be a big problem. There used to be scalability issues with Lambda inside the VPC, but that has been a thing of the past for quite a few years. So it's not really a showstopper. You should not use this as an argument if you're an architect against using a relational database. It's just being a little bit lazy, to be honest. Okay, our final point. So if relational databases have any self-esteem left, we're going to completely empty it now. And this is a biggie, that relational database pricing doesn't scale to zero. So I have a very non-scientific graph on the right-hand side, but I just want to show the relationships. DynamoDB being our blue line, it's linear. If you double the amount of requests you want to send to your database, your cost is going to double. It's a linear relationship. Whereas with our red line, which is for Aurora Serverless version 2, let me do some definitions. So Aurora is AWS's own database engine that they created. It's fully compatible with MySQL and Postgres. That's a bit more cloud friendly. We're not running everything in a box. They have a serverless option where the amount of compute that your database tier needs to process the requests is something that scales with your use. And there's a concept of an ACU, an Aurora Compute Unit. I'm sure we've seen these acronyms all over DynamoDB, and I heard it in the OpenSearch talk just now. Basically, as you increase the amount of requests you want to pass to your database, the managed service needs to provision more ACUs. Every time you provision one, that's where we see a step on the graph. Now, that's focused right at the bottom left of the graph. This is where the problem lies. With Aurora Serverless v2, the minimum amount that you can provision is not 0, it is 0.5. It's half an Aurora Compute Unit, which equates to about $30 a month. So that has all sorts of knock-on effects for POCing and ephemeral environments, which we'll come to in a bit. But for now, it's something we don't like. Again, we could go back to that graph or that table of all of our components, ask which of those scale to 0, and we would have had the same result. Okay, I think we move on. Okay, so let's sort of summarize this section. I've told you about all these things that are wrong with relational databases. They don't scale. They're slow. They have to run in a VPC. And they don't have a pricing scale that goes to 0. So now I ask all of you here, why are you here? Why are we trying to shoehorn a relational database service into our serverless applications? There's four fairly concrete arguments against doing it. So let's now turn the tide and let me highlight some examples of when we should be reusing our relational databases. We have a couple of easy ones. If you're in those highly compliant industries, you need to use software that your compliant regulations allow. I talked about asset compliance earlier. And so a lot of these databases, as I said, they're software that was first created in the 90s. It's very safe. The regulators like it. I don't think many banking applications are going to be using things like DynamoDB behind the scenes. So as an architect, if you're in that situation, you should not be trying to force any new applications into DynamoDB. You need to respect your requirements. The next point, migrating legacy applications. That's not creating more work for our developers. Having to move from one database architecture to another is a huge pain. Sometimes there is not the return on investment that you think you may have. Now, actually thinking about the nature of the data itself, something that is very easily, very commonly overlooked when designing applications. Is it relational? Do you have data in one table that needs to be, that you need to sort of compare with data in another table? If you're, for example, you have a table full of users for your application, and then you have orders for an application, and you want an API to say, okay, for John Smith, retrieve all my orders, the application needs to go to your first table to find the ID of John Smith, and then go to another table to find, okay, what orders match that ID. In relational databases, simple join. DynamoDB, unless you've created a complex single table architecture or composite keys, just for this one use case, you'd have to do 2 database requests. We're going to come to some pricing examples in a second, and so bear that in mind. Sometimes I need to tell my clients that you have to do 2 database requests for 1 transaction, doubling your cost. And then finally, knowing your access patterns. We spoke earlier about our analogy that our databases are a bit like running a bar. If you turn up halftime in your sports event and ask for a margarita, the person's going to shrug and just give you a beer. However, if you go to a cocktail bar and you ask for that pint, they might have one on draft. They're not too happy about it, but they'll serve you a pint. That's fine. They're a lot more flexible with their access patterns. And as your requirements change over time, and I see this time and time again with DynamoDB, if you haven't designed the table for what's coming in the future, it can really bite you because you have very, very strict access patterns. Something else to consider. DynamoDB is strongly opinionated. It's a newer bit of technology. It's got less legacy use cases and legacy code to work with. So they implemented their own service limits that we have to respect. 2 here that I want to highlight. Let's start with the item size limit for DynamoDB, 400 kilobytes. If you have a single item that wants to be 401 kilobytes in size, it is not going to work. It is not going to persist. There is no support ticket you can raise. That is a hard limit. So over time, as your application grows, maybe you're storing some stringified JSON. And over time, the business wants to add more and more keys in here. You think, okay, that's fine. A few years later, one user with a particularly long name or ID brings their item to greater than 400 kilobytes, and it just doesn't work. You don't have that problem with relational databases, a lot more flexible. The other point, right in the top left, we have the request body size for DynamoDB. So this is specifically for if you want to do a batch set of writings. You want to write lots of items all at once. You're restricted in each request to a maximum of 25 items. So just imagine if you've been asked to take data from one place, move it into this DynamoDB table. You say, okay, how much is it? And oh, 10,000 users. Oh, okay, that's going to take a long time. It's going to be expensive. And you've got to handle all sorts of throttling and whatnot. With a relational database, you can run these long-running requests that are flexible, and so it's a little bit easier to work with. Now we're going to come to a pricing scenario. I want to give you a real scenario comparing these 2 database options, DynamoDB, and we're going to use Aurora Serverless v2. The reason being is it's the closest in terms of comparison. They both scale with the amount of, they more or less scale with the amount of requests that you fire at it. They both scale with the amount of storage. So the pricing model is similar. In this scenario here, we're going to assume that all of our items are exactly 4 kilobytes. This is doing a favor for DynamoDB. If it was 4.1 kilobytes, everything you see here is going to double. We're going to assume that we're doing 500 TPS, that's transactions per second. So we're going to be trying to do 500 read transactions every second. And we're going to assume the database has got about 100,000 items, so it's about 400 gig. We're going to go over this slide just very quickly because we're going to actually compare the slides in a minute or so. But the key thing I just want to point out here, first of all, very, very hard pricing databases. DynamoDB has quite a nice pricing model. It's relatively easy as a solution architect to tell my clients how much it'll cost. Relational databases, not so much. I may be able to eyeball the sort of the instance size or the amount of ACUs, but it's difficult and it comes with experience. Now, this price for requests, when it comes to Aurora Serverless v2, this is an IO request. It's basically, you get charged 20 cents, it's 20 cents, not 2 cents, for every million requests that have to go all the way to the IO, all the way to the storage. Aurora Serverless v2, it has this magical caching layer that we don't really see too much documentation for. In this scenario, I'm going to assume that 10% of our reads hit the cache. 90% have to go all the way through. Okay, so that's why we brought it down by a factor of 10 to 2 cents. Now, let's see how much this actually costs. So, over the space of a month, 1.3 billion requests are made. Remember, it's 500 every second. DynamoDB, let's look at let's start with the storage. 400 gigabyte, here's a cool fact for you. The pound per pound, byte for byte, gigabyte for gigabyte, is much cheaper in a relational database versus DynamoDB. These options are using on demand. They both have sort of savings plans or provision modes that can reduce that cost. I'm just trying to keep the comparison as easy as possible. So that's one thing. The compute, as I said, you have to kind of eyeball these things for relational databases. From my experience, something like this, 5 ACUs. That equates to 5 vCPUs and about 10 gigabytes of RAM. So somewhere between a large and extra large instance if we were trying to compare that to RDS. Speaking of RDS on the right-hand side, I wanted to use a traditional provision RDS here just for comparison between the two. And since we want high availability, we will need 2 instances. Okay, so we can see at the bottom, we have our totals. DynamoDB does slightly win in this scenario. So let's give round 1 to DynamoDB. Now let's look at a second scenario, a write scenario. This time, everything's the same, 4 kilobytes, 100,000 items. But this time, we're going to do 50 writes per second. Instead of 500 reads, 50 writes. Now, let's see how the pricing changes. DynamoDB, for our price per million requests, goes up by a factor of 20. That's for 2 reasons. Our WRUs, our write request units, they do cost more than a read request unit. On top of that, the threshold for when an item should be charged at 1 or 2, it drops from 4 kilobytes to 1. So not only are we paying a little bit more, but we're now being charged 4 times, 4 write request units for every write. And you can see that scales to $5 per million. Comparing that with Serverless v2, because we're doing writes, we're never using the cache. So we can assume that we're going to be going all the way through to the persistence layer. And so it's 20 cents per million. Now, let's take a look at some numbers and see how things have changed. DynamoDB, that request, of course, we expected that to skyrocket. Obviously, it hasn't gone up 20 times because we're doing 1/20th of the request, or 1/10 of the requests. Doing 50 transactions per second instead of 500. From my experience, running with 50 writes per second only requires 3 ACUs for our Aurora Serverless v2, so that brings the compute down a little bit there. And now we look at the totals, we can see there's a huge difference between for a write-heavy scenario, using DynamoDB versus relational databases. And so finally, let's combine the two. It's very common that your database scenario needs to do both. So let's do 500 reads and 50 writes. And the good news is we can just add everything together. We've just done the maths. And this is what we see. DynamoDB versus Aurora Serverless, you can see that you've got a huge noticeable price reduction when using Aurora Serverless v2 in this particular scenario. I can't emphasize enough how difficult it is to compare databases. It is like comparing apples and oranges. It literally is. But for this very simple scenario, we can see a very noticeable change. As a solution architect, I need to identify when it would be cheaper to go with a relational database. Now, some of you may have looked at that third column for a traditional provisioned RDS and see the price and thought, well, that's even better than the other two. So should I maybe use that instead? My counter argument to that is that what we've done here is we've assumed a completely flat amount of requests. So in total, 550 transactions per second. So if you can fully utilize your provisioned instance, then great. Most of the time, provisioning not using those pay-as-you-go models, using something pre-provisioned for a consistent known amount of traffic will be cheaper. However, in reality, whatever application this is, it's probably got its peaks and it's got its troughs. So in reality, you would need to provision more, provision less. There will be some loss there. So we're just comparing DynamoDB and Serverless v2. So that brings us to the third part of our talk now. I've covered everything that's wrong with relational databases. I've shown you there are some scenarios you should consider. There are limitations you need to be aware of. And then I've shown you that it can actually be cheaper. Now, you made that decision to go with relational databases. And this is where I take off my architecture hat and I put on my developer hat, because it's not fun to work with. But there are tools, there are services, there are third parties that are either great now, need a little bit of work, or are genuinely emerging in the coming months. First of which is ORMs. So I mentioned right at the start, when I became that DevOps engineer, I was working with Python applications using the Django framework. So Django provides an ORM. For those that aren't aware what that means, it means that you don't need to think about the SQL query language. You instead just manage the program level objects, and that somehow, with some magic behind the curtains, gets converted into items in the database. Serverless applications, one of their main drawing points is how easy it is to use. You don't need to write lots of code. You focus on business logic. And we don't see too many ORMs being used in examples and in documentation in the community. And there are genuinely reasons for that. One of which, most, not all, but most examples use JavaScript. JavaScript is a loosely typed language. So if you're providing some kind of model for your data and saying, okay, create programmatic objects of this nature, well, in JavaScript, I can just add a new attribute and the code won't fail, but it's not particularly useful when it comes to persisting that data. I cannot take that attribute and just throw it into the database. It needs to be well defined in a model. For things like Python and TypeScript emerging a lot more common, you see a bit more traction with ORMs. But they have a few other problems. Let's use Django as my example. We have use the CLI to actually do these migrations of the tables. We have these models where we define our objects. What happens when they change? You need to run some SQL somewhere on your database to update those tables. Typically, you'd run that on your server because Python Django applications, they're designed to run in the box. So either part of your CI/CD, or somebody might do it by hand in production, or you automate it. You go on that machine because it can already talk to your database. It's on the network, and just run a simple command. The serverless application, we've got these Lambda functions running somewhere, probably running in a VPC. I don't know about you, but it's very hard to get onto the terminal of a Lambda function. It's not really designed for that. So the way that I've seen that problem solved is people writing Lambda functions just to do the migrations. So you're writing more application code just to facilitate your application code. That's a gap. That's something that needs to be filled. Somebody needs to build an ORM that's a bit more serverless-centric. The final part, they blow your Lambda package. ORMs contain a lot of code. They're doing a lot of magic behind the scenes. And let me give you an example. Prisma. Prisma is one of those popular ORMs when it comes to JavaScript, and its package size is 10 megabytes. That's 4% of the entire quota of a Lambda package. So your Lambda cannot be bigger than 250 meg, I believe. That's 4%. That's moving the needle before you've even added any runtime or AWS SDK or any of your business code. You've lost 4% of your allocation already. The main issue with that is going to cause some more cold starts. Not a huge deal, but if you're working with something very low latency, where you want to be spinning up Lambdas and running them just like that, you will notice that with ORMs. Next up, we have the Data API. Data API is a way of circumventing the need to use the network. It exposes a HTTP endpoint, very similar to DynamoDB. And when I saw that, I thought, great, I can run my Lambda functions outside the cloud. I can do outside a VPC. I can run my Lambdas locally and talk to my database. Then there's all the pricing for it, and no, you cannot use the data API at scale. So rather than having your cake and eating it, meaning that I can use a relational database, circumvent VPCs, it's more like, it works. There we go. Having your cupcake and eating it. Do not use the data API at scale. It's not designed to replace a database client. Speaking of publicly exposed databases, because this is now exposing a HTTP endpoint for your database, there are some third parties that are doing some exciting stuff. I'll show on the final slide coming up next, Zata, Neon, and Superbase. And the common thing here is that they're a third party. They cannot integrate into your VPC, so they expose something, and it's kind of scary. I've always been told databases, private subnets, never public subnets. The attack surface area is massive, and it's mission critical for your applications. So I see this, and I'm kind of worried. I won't lie. But they're new, they're emerging, and I'm sure they're going to find ways to circumvent this. So the final point on ephemeral environments. Now, this is one of the great selling points of serverless applications. Ephemeral environments. I'm a developer working on a feature. Just spin everything up. A DynamoDB, your Lambdas, your API gateways. Just spin it up because it's pay as you use, and you're just one developer. When you go home at night, you're not running any requests, not spun up any containers. It's not going to cost anything. Now, when you have relational databases, let's think back to one of those key points against them, the pricing structure. They don't scale to zero. So each ephemeral environment, assuming you're using, for example, Aurora Serverless v2, that's $30 per month per ephemeral environment. If you're not doing anything, you still have half an ACU provisioned. Now, there are tips here to allow you to use ephemeral environments in serverless stacks that have relational databases. The first problem, which I kind of spoke about with ORM, is how do you create all these tables? It's complicated. You need to run this code somewhere. And this is where, now linking the previous slides on the data API, this is a great use case. Just imagine as part of your CI/CD, you want to run some integration testing to spin everything up. Okay, we're going to spin up a relational database, more on that in a second. I need to seed it. I need to maybe create some tables and actually put data in there. Now, how can you do that from CI/CD? We have the data API. Remember, I just told you what it was? So it's a HTTP exposed endpoint, and it's authorized and authenticated with IAM, the exact same way DynamoDB works. So there's no real security concern. The only problem I said, don't use it in your applications at scale. But we're in our CI/CD, and we just need to run this a few times a day, maybe 100 times a day. That price isn't really going to be noticed. So that's a great way of avoiding having to write your own Lambdas and deploy those and provision those and invoke them, and they're inside the VPC just because you're trying to circumvent all this networking. Now, second point here on some of these third parties, Zata and Neon, they've got this great trend that I really love for serverless applications. They have a feature called branching. So in a similar way to how we have Git and we have branches off of Git for features and whatnot, they support doing the same thing for your databases. You have a database for this table, and you can simply branch that to a carbon copy of it, and then you can run that and use it for whatever you want. So how does that work? In your CI/CD, somebody maintains a golden template containing the initial state of your data you want all your tests to run in. As part of CI/CD, you would create a branch just using the services APIs, and then you would just use that table as part of your integration tests. You'll be inserting, deleting, updating, I'm sure, and at the end, you can just delete it, and it just deletes like that. So it makes using ephemeral environments a lot more developer friendly. I think that brings us to the end. Thanks so much for your talk. I hope for some of you, I may have convinced you to think otherwise before going straight into the Lambda DynamoDB trends that we see everywhere in documentation. And let's give relational databases a fair trial.